Hello, everyone. Welcome to our Statistics Solutions webinar. My name is Justin D'Souza. Today, we'll be conducting a webinar on ANOVAs. So we'll be going through how to set them up and how to interpret them. If you have any questions, you can type them into the chat box or the Q&A box. And at the end of the webinar today, I will be doing a Q&A session. And we'll be sending everyone a copy of the PowerPoint, as well as a copy of the recording of today's webinar. First, I'll give a brief overview of the services we provide at Statistics Solutions. Then we'll dive into ANOVAs, how to conduct them, what assumption checks to check, and how to interpret. I'll give a brief demonstration in our software, our company software, which is Untitled Statistics. And then we'll conclude with a summary and a Q&A session. So on this slide, you can see all the various topics and parts of the dissertation that we assist with. The way our company works is we will assign both a statistician to you. We have methodologists, both quantitative and qualitative, and we also have literature review specialists. So depending on where you need assistance, you may receive one specialist or multiple. We help with all the proposal chapters, the intro, lit review, and methodology. Some universities have a prospectus or a concept paper, which goes before even the proposal. So if you need help with topic development or framing research questions, identifying a theoretical framework, we can help you with those chapters. We also help with the IRB process. If you need help completing your IRB forms, we can help with a data entry template if you're not sure how to organize your spreadsheet. And we can host a survey for you on our own SurveyMonkey account. Then once you're done with the proposal, we can help you with the results chapter, both quantitative, qualitative, or if you're doing a mixed method study. And we assist with the discussion chapter, PowerPoints for proposal and final defenses. And we can help condense your dissertation into a journal so you can submit to a publication. If you have any questions about the services, you can give us a call for a free consultation at 727-442-4290. So first, we're going to discuss ANOVAs. I'm going to focus on two primary approaches for ANOVAs, both an analysis of variance and a repeated measures analysis of variance. Excuse me, I'm a little bit sick, so I'm a bit nasally. If I'm speaking too soft, just let me know. So an ANOVA is used when you're assessing for differences. That's the key word. We're assessing for differences in a continuous variable between two or more independent groups. Okay, so when you're setting up an ANOVA, you need to have an independent grouping variable that has at least two discrete groups. And I say two plus or two or more discrete groups because you could have only two groups. But in that scenario, you should probably just do an independent t-test. It's a little simpler, a little more straightforward. But if you have two or more, usually three groups or more, you can do an ANOVA. And discrete means that each participant only falls into one group. Okay, so you can't have overlap into multiple groups. For example, if you're looking at comparisons between classes and you have class A, B, C, D, and so forth, you couldn't have a student that is in multiple classes. On this test, they need to be in only one group. Another common example would be ethnicity: white, Black, Asian, Hispanic, other. And if you're doing an experiment and you have treatment and control groups, that's another common occurrence to an ANOVA. Next, you need to have a continuous dependent variable. So this is essentially a numeric variable. It can be a composite score from a Likert scale survey. It could be test scores. Essentially, you need a quantifiable numeric variable to do an ANOVA, and that is your dependent variable. Then you'll want to review what assumption you're going to check. Every inferential analysis has that you need to verify before you run the analysis itself. So So in ANOVA, we'll go to the website here, which is a very popular website today. I see a lot of universities referencing this. Statistics Layered is the company. So you can scroll down and kind of identify what an ANOVA is, how to set it up, and what assumptions to check. We can see here assumption 1, 2, 3, there are 6 of them. And the first couple are just kind of definition based. We already went through this, that you need to have a dependent variable that is continuous, essentially meaning that they are interval or ratio level variables. The second assumption is that you have 2 or more categorical variables, also called nominal variables. Assumption 3 is independence of observations. So this is kind of going into the idea of discreteness. You can't have overlap between your participants and what groups they are in. Then you should check for outliers. You don't want to have outlying cases in your spreadsheet for the test scores or the Likert scale data. You want to remove outliers because that can skew the findings of your ANOVA. The next assumption, and I would say probably the most important one, is that your data are normally distributed. So you need to have a dependent variable that follows a bell-shaped distribution or a bell-shaped curve. If it does not, we'll touch on that in the PowerPoint. There are backup approaches that you can use. And the final assumption is homogeneity of variance. This is making sure that the standard deviations or the spread of your data is approximately equal between your groups. Okay. Okay, and once you've checked the assumptions, you can then run your analysis in whatever software you choose. SPSS, Stata, SAS, Intellectus Statistics is what I will show a demonstration in, which is our company software. The next repeated measures ANOVA is what we're going to look at, is when you're looking at differences between matched continuous variables. So that's if you have most likely an intervention at some point in the middle of your study. You have a pre-test, you administer an intervention, and then you measure a post-test. If you only have 2 points in time, then you might as well just do a paired t-test if you just have a pre and a post. But if you have 3 or more points in time, a pre-test or a baseline, then a post-test, then a follow-up at some point in the future, that's when a repeated measures ANOVA is the best option. Set this up, you need to have one match dependent variable that, excuse me, that is measured at least 2 times. So pre-test, post-test, follow-up. The important idea behind this is that you are bringing back the same people who did the baseline or pre-test. So you need to match your participants if that's done with an ID, a numeric value, or you're using email addresses maybe. You need to match your participants to do this test. Then you can check for the assumptions, very much like the ANOVA we just reviewed for a repeated measures ANOVA. Statistics Layered also has a breakdown on how to run this test and what assumptions. Repeated measures ANOVAs I see most often are used in the nursing field. If you're doing a biology study, that's usually when you have an intervention. So this one has very similar assumptions. Your dependent variable needs to be continuous. The independent variable here is the idea that you have matched data, that your pre-test participants are coming back to the post-test. Again, there should be no significant outliers. And then we have that the distribution of the dependent variable is normal once again. Okay, so there are many ways to check for normality. Again, this is probably the most important one because if normality is not supported, then you might have to shift to a different approach. And the last assumption is sphericity. And this is making sure that the spread of your data is approximately equal across your time periods. So your standard deviation and your variance is approximately equal between pre-test, post-test, and follow-up. Okay, so let's dive into the normality assumption, because I've said a couple times this is quite an important one. Normality is making sure that your data follows a bell-shaped distribution. And there are many ways to check for this. It's a prerequisite for a lot of inferential analyses. If you're doing t-tests, ANOVAs, regressions, you have to check for normality. So it's important, I would say, to check with your committee, because your committee is going to have a preference what way to check for normality. There are numerous ways you can do it. The most common I see are Shapiro-Wilk and Kolmogorov-Smirnov tests, but you can also look at skewness and kurtosis, and you can visually look at normality with scatter plots or histograms. If the data do not follow a normal distribution, then the most common approach is to go to a non-parametric technique. Most parametric analyses have a non-parametric alternative, and non-parametric statistics are not so reliant or contingent on a bell-shaped curve. We'll discuss those. The alternative is if you have a large sample size, then you can use the central limit theorem to justify proceeding with your ANOVA t-tests or regressions, even if the normality assumption is violated. So the central limit theorem basically says that the larger your sample is, the more it resembles a bell-shaped curve. So I provided a citation here. Howell, he indicates that if you have at least 50 cases, then your sample size is sufficient to proceed with parametric analyses. But if you're below that, then you might want to consider going to a non-parametric technique. You can even consider transforming your data. So transform it into a logarithmic or a quadratic or cubic function. Sometimes that fixes it. I try to avoid transformations because it gets a little confusing to interpret. Okay, so for the ANOVA, as we've defined, is looking at differences in a continuous variable between groups. A non-parametric alternative to this is called the Kruskal-Wallis test. So for one thing, it can be used if normality is not supported, but this is also used if you're looking at an ordinal variable, just like a single Likert scale question, strongly agree to strongly disagree. If you're looking at a dependent variable that's ordinal between groups, then you can run a Kruskal-Wallis. When looking at differences in time, like the repeated measures ANOVA, the non-parametric technique for this is a Friedman ANOVA. And again, you can use this when normality is not supported, or when you have an ordinal dependent variable, like the Likert scale question. Okay, so let's take a look at Intellectus here. This is what Intellectus looks like. The first thing you can do is you can upload a spreadsheet. You can upload a CSV, Excel file, SPSS, SAS, or Stata file. I have an example here already uploaded. So I'll click Load Project. This is what the data looks like. You can see that what we have are test scores by classes. So we have reading that was measured at pre-test, then it was measured in the winter, and then it was measured in the spring. And then we have math scores and science scores. We have the sex or gender of our participants, along with multiple classes. We have class A, class B, and classroom C. So here you can see some data management functions that we have in the software. You can change your levels of measurement. If something is not scale, you can change it to nominal or ordinal. Everything is accurate here. You can reverse code items. If you have negatively phrased Likert scale data, you can reverse code. You can remove outliers. So that's something we should do here. That's one of the assumptions of an ANOVA. Right here is the fourth one, is that there are no significant outliers. So you can quickly do that here if you go to remove univariate outliers and then just select all the variables of interest. Submit. And what this will do, if there are outliers, it's going to leave a blank in the cell. And just scrolling down here, I actually do not see any cases. So all the data in here are acceptable. We do not have any outliers in this data. So that assumption is supported. And I mentioned transformations earlier. If you wanted to change the transformation of your data or change it to a different distribution, you can change it to these different options. Sometimes that helps meet the normality assumption. We'll go to analyses here and let's run an ANOVA. Okay, so hypothetically, what if our research question was, is there a significant difference in math scores based on what class the student is in? So because we have a continuous dependent variable of math scores, we have a categorical variable of class, and there's no overlap. Every student falls into one class, and we have 3 classes. This is when you do an ANOVA. Okay, so I'll go to ANOVAs and ANOVA. Our dependent variable is the variable we're trying to see differences in. Click right here, we'll do math, confirm, and our independent variable is the grouping variable, which in this case will be class. You can see at the top right here, we have options, and you can see what is going to be presented in the output. Usually I enable Shapiro-Wilk test, which is a test for normality. And we have Levine's test, which is a test for homogeneity of variance. So coming back here, Shapiro-Wilk is going to look at the normality assumption. They even mentioned that right here. So Shapiro-Wilk test of normality. And the last assumption is homogeneity of variance, and we're going to use Levine's test. The software has all of this built in already. And I'm also going to enable automatic nonparametrics. What this will do is if any assumption is not supported, Intellectus will automatically run the nonparametric equivalent to that test. So as I said earlier here, if normality was not supported on the ANOVA, Intellectus would automatically run this backup Kruskal-Wallis. So the options look good. Click calculate. And this is going to provide a full APA write-up with interpretations and APA tables and figures. The first thing it does is it gives a breakdown of what the analysis is doing. We can see, are there differences in math by class? Then we check for assumptions. The Shapiro-Wilk test is looking at normality. And for this test and for Levine's test, we hope for a non-significant result, meaning we hope we have a p-value greater than 0.05. If you hover your mouse over the terms, it tells you what they mean. So if you have a non-significant result on this test, as we do, that means that your data for math scores resembles a bell-shaped curve, and the assumption is supported. Same idea with homogeneity of variance. We're hoping for a non-significant result. And what that means is that the math scores are evenly spread out based on class, which is what we want. So that assumption is supported. Then we come down here, and there's a lot of statistics, but the most important thing is the p-value. This is the result of the ANOVA, and if the p-value is below 0.05, that indicates that we have significant differences by group. In this case, we have significant differences in math by class. And we can see a bar chart here. You can see what class performed the best, what class performed the worst, and so forth. And because we have significance, that isn't quite enough. We want to know what class performed better than the other classes. So we have to dive a little bit further in, and we need to do post hoc tests. Post hoc tests are going to compare every class to every other class. Class A to B, class A to C, and class B to C. And what the result found is that right here, you can see it gives you a p-value for class A to B. This is a significant result, meaning that class A scored significantly higher on math in comparison to class B. And likewise with class B to class C, we have a significant result again. This is below 0.05. Class C performed significantly better than class B. The one we're missing here is class A to class C. So this comparison right here, class A to class C, there was a difference, maybe a talking point for your paper, but it wasn't a statistically significant. Okay, so that's a ANOVA. Now, we also have these reading scores that have been matched. We have reading pre-test, reading post-test, and a follow-up. So this is a perfect time to do a repeated measures ANOVA because we have 3 points in time that have been matched. We go to analyses, and repeated measures ANOVA is right here. The dependent variables will be reading pre, post, and follow-up. That is it. We'll go to options, and you can see again, we're checking for normality, Shapiro-Wilk test. Sphericity is an important assumption for this one as well. It was assumption 5 right here. And again, I will enable non-parametrics. Save the options and click calculate. Should take 10 to 15 seconds at the most. Here we go. All right, so first, again, we get a breakdown on the analysis. We're doing a repeated measures ANOVA on reading 1, 2, and 3. Then we verify for normality. Now, in this case, we can see we have a significant result, which is not ideal. We don't want a significant finding on this Shapiro-Wilk test, meaning that the data does not follow a bell-shaped curve. Okay, so normality was not supported and sphericity was also not supported. So as we can see here, significance for assumption checking is not ideal. You want non-significant findings. So what this is going to do, because the assumptions were not met, it's going to report the repeated measures ANOVA. But as I reported here in the PowerPoint, if the assumptions are not supported, you should run a non-parametric backup. In this case, a Friedman ANOVA. Because the assumptions were not met, it's going to run that test automatically right here. So you can see one or more of the assumptions were violated. Therefore, we're going to run this backup test just to confirm the findings. And usually the findings will align. If you see significance on an ANOVA, you usually will see significance on the backup test as well. Okay, so coming back to the ANOVA, this is the most important line right here. And the p-value right here tells us that we have a significant change in reading over time. Okay, so we do have a significant difference in our reading scores between pre, post, and follow-up. Now, again, that's not quite enough information. We want to know, was pre different than post different than follow-up, and what about the comparison for pre and follow-up? We need to scroll down a little bit more. We have a line chart to show the differences over time. But again, we need these post hoc comparisons to look at each time period compared to every other time period. And we can see every single one was significant. Okay, so reading pre to reading post, we have a p-value that is below 0.05, indicating that there was a significant change over time. Same with pre to follow-up, and same with post to follow-up. All three are showing a significant change over time. Then we come down here, and this is our Friedman ANOVA, which was run because normality and sphericity were not supported up here. And this test also shows a significant change over time. It does a slightly different calculation. It doesn't look at means. Instead, it looks at mean ranks. Okay, and we can see that there is a difference over time. The mean ranks appear to be increasing with each test. And then the pairwise differences are at the bottom again. Okay, so is there a difference between pre and post? The way you do this is you compare your observed difference to your critical difference. And if the observed difference is greater than the critical difference, then we have a significant change. So we can see in every case, the observed is larger than the critical difference. Therefore, we have confirmed what the repeated measures ANOVA found. So even despite normality not being supported, we found a significant change, and our backup test found the same result. Okay, and we do have other options here. We have ANOVAs, which are used when you have multiple dependent variables. The first test I did was, is there a difference in math by class? But say I wanted to look at math and science at the same time, that's when you do a MANOVA. When you have more than one dependent variable, that's when you do a MANOVA, which just means multiple analysis of variance or multivariate analysis of variance. And so for a MANOVA, same process. Instead of just selecting one variable, you can select multiple. We'll do math and science. And we'll do class. Okay. The first thing it does is it's going to check for collective differences. Okay, so it gives you a p-value right here. I didn't do the assumption checking for this one, but you would do the same process. Just enable the assumption checks that you need to. I'm jumping ahead just for interpretation. So this p-value here is a multivariate p-value, and it's telling you do math and science together here to have a difference by class. And this, again, is a significant finding. So then what it runs is a separate ANOVA for each variable. First, it's going to do an ANOVA for math by class. And this is going to be the exact same finding as we did up here. Okay, so we have F was 7.63. And here's the MANOVA, F is 7.63. But now we have science that has been added. So it does a separate ANOVA for science by class. And again, we see a significant change. And you can see how the scores changed over time. Okay, and there are many other options. You can give us a call if you have any questions about them. You can introduce control variables or covariates if you do an ANCOVA. If you're doing a true experimental study, like a pre and post with a treatment and control group, that is usually when you do a mixed model ANOVA, because you have differences over time and you have differences by groups. Okay, so essentially you have to identify your independent grouping variables and your dependent variables. Do you have one dependent variable or multiple? Are you looking for differences by groups, or are you looking for differences over time? Maybe both at the same time. Then you can use SPSS or Intellectus to analyze your data. I'll now open up the panel for questions if we have any. If you have questions about the presentation or about the services we offer, you can type those into the chat box. We'll send everyone a copy of this as well. And we had a question from Crystal asking how much does the software cost? It's $59 a month, and there is a 7-day free trial. Okay, so much more cost efficient than SPSS. And it's going to give you a full interpretation of your data as well and present it in APA format. right, do we have any questions? You can raise your hand as well. All right, well, excellent. Thank you so much for joining, everyone. We do about 8 of these webinars a month covering different topics. Come join us for the future sessions and let us know if you have any questions. Have a great evening.